Welcome to a crucial module on building reliable software, unit testing. Writing tests is the backbone of professional programming, ensuring that your code works as intended, remains functional as you make changes, and simplifies the debugging process. We will be focusing on Python's built-in unit test module. 1. What is a unit test? In programming, a unit is the smallest testable piece of code, usually a function or a method. A unit test is a written block of code that checks if a specific unit of your application is working correctly, isolated from the rest of the system. 2. Why do we write tests? The primary reason is verification and regression prevention. Verification means confirming your code meets its requirements. Regression prevention is critical. If you change one part of the code, a robust test suite immediately tells you if that change broke functionality elsewhere, saving countless hours of manual debugging. It is the safety net for refactoring. 3. The Python unit test framework. Python's standard library includes the unit test framework, which is inspired by JUnit. All tests are organized into classes that inherit from unit_test_case. Each test method within the class must begin with the word test_. Inside these methods, you use assertion methods like assert equal to verify that an expected result matches the actual result. To summarize, testing is essential. Now let's write our first test. Our next lecture 34.02. Create and run a test. See you there. Welcome back. In this lecture, we will move from theory to practice by creating a simple function and writing our first unit test for it. We will cover the correct file structure, the basic test assertion, and how to execute the test suite from your terminal. 1. The code under test. First, we need the code we want to test. We'll create a file named calculations.py with two simple functions, add and subtract. For this lecture, we will focus on writing tests for the add function. 2. Writing the test file. Following best practices, we create a separate file, typically named starting with test_, here test_calculations.py. We import unit_test and the add function. Our test class inherits from unit_test_case. We write two methods, both starting with test_, using the key assertion method self.assert equal to compare the actual output of our function with the expected output. 3. Running the test suite. The simplest way to run the tests is by executing the test file directly using Python, thanks to the if __name__= _main__ unit_test.main block. The output shows two dots, indicating two tests ran successfully, followed by a summary line confirming that the results are OK. To summarize, you can now write and execute basic unit tests. Next, we look at how to test for failures. Our next lecture 34.03. Assert for exceptions. See you there. Welcome back. Good software doesn't just work when given valid input. It also handles invalid input gracefully by raising appropriate exceptions. In this lecture, we learn how to write tests that specifically verify our functions raise the expected exceptions using assert raises. 1. the code that raises an exception. Let's update our calculations.py file with a new divide function. This function explicitly checks for division by 0 and raises a 0 division error if the denominator b is 0. We must write a test to ensure this defensive coding works correctly. 2. Using self.assert raises. We use the self.assert raises method as a context manager with the with keyword. You pass the expected exception type, here 0 division error, as the argument. Any code executed inside this with block is expected to raise that specific exception. If it does, the test passes. If the code executes without raising the exception, or raises a different exception, the test fails. 3. Capturing the exception message, optional. For more rigorous testing, you can capture the raised exception object by assigning the context manager to a variable, here, context. You can then access the exception using context.exception and assert that the error message it contains matches your expectation. This ensures not only that the right error is raised, but also that the user receives the correct descriptive message. To summarize, testing for exceptions is crucial for validating the defensive capabilities of your code. Next, we look at managing test state. Our next lecture 34.04, Setup and Tear Down. See you there. Welcome back. In many testing scenarios, you need to perform the exact same setup steps, like creating a temporary file or initializing an object before every test. Similarly, you need to clean up those resources afterwards. In this lecture, we introduce the setup and teardown methods provided by the Unitist framework to manage this test lifecycle. 1. The need for setup and cleanup. Imagine you are testing a class that manages a database connection. You don't want to manually connect to the database in every test method, and you certainly don't want to leave open connections or temporary data cluttering your system. The setup and teardown methods are explicitly designed to handle this boilerplate setup and cleanup, ensuring each test runs in a clean, identical environment. 2. Implementing setup. The setup method is called automatically by the Unitist framework before every single test method in the class is executed. Here, we create an instance variable self.userdate, which is accessible by all the test methods. This ensures that every test starts with a fresh copy of the necessary initial data, preventing tests from affecting each other. 3. Implementing teardown. Conversely, the teardown method is called after every single test method, even if the test fails. It is used to release any resources acquired in setup. In a real-world scenario, this is where you would close database connections, delete temporary files, or reset global settings to ensure isolation and a clean system state. To summarize, setup and teardown guarantee test isolation and a reproducible environment. Our next lecture 34.05, Assignment. See you there. We have covered the core components of Python's Unitist framework, basic assertions, testing for exceptions, and managing resources with setup and teardown. Now it's time to apply these skills to a practical assignment. You will be testing a simple class designed to manage user tasks. 1. The Task Manager class. Your code under test is this simple Task Manager class, located in taskmanager.py. It has methods to initialize an empty task list, add a task, remove a task, and retrieve all tasks. Note that the remove task method raises a value error if the task does not exist. Your goal is to test all these functionalities. Two, assignment requirements. Create a file named test_taskmanager.py and write a test class. You must cover 4 specific requirements. First, use the setup method to initialize a new instance of the task manager class before every test. Second, write a test using self.assert equal to check if a task is added correctly and the length of the list is updated. Third, write a test using self.assert raises to confirm that removing a non-existent task raises a value error. Fourth, optionally, you can use tearDown to check that the instance is properly cleaned up after tests. To summarize, start by setting up the instance in Setup, then create tests for successful addition and failed removal. Good luck! Our next lecture 34.06, Documentation. See you there. Welcome to the final lecture in our module on unit testing. We've learned how to write, run, and manage tests. The last critical step is documentation. Well-documented tests are just as important as documented production code, ensuring that other developers or your future self understand the test's intent and purpose. 1. Test method naming convention. The most basic form of test documentation is a clear, descriptive method name. The name should read like a sentence describing the exact scenario being tested, the input condition, and the expected outcome. Good naming eliminates ambiguity and allows anyone to instantly grasp the test's objective without reading the code inside the method. 2. Using docstrings for detailed context. For tests involving complex setups or subtle logic, adding a docstring is necessary. The docstring provides a concise summary of the test's specific goal, the preconditions, and any potential side effects. This documentation is crucial when debugging test failures, especially in large code bases. 3. Docstrings in test reports. Docstrings aren't just for reading the source code. Many advanced testing tools, like Nose2 or PyTest, can optionally use the test docstrings to generate highly readable, human-friendly test reports, transforming cryptic test failures into clear, descriptive messages for the entire team. This capability underscores the value of writing good docstrings. To summarize, think of test documentation as code maintenance for your safety net. This concludes our module on unit testing. Our next lecture starts a new and exciting module, 35.01, Introduction to NumberPy. See you there.